For centuries, the world's oceans were dominated by ships, whose power was measured in the thickness of their steel plating and the diameter of their massive guns. The battleship was the ultimate arbiter of global supremacy, a floating mountain of artillery designed to slug it out in brutal broadside-to-broadside engagements. However, the dawn of the 20th century brought a fragile invention of wood and canvas that would entirely dismantle this ancient maritime order, the airplane. In the years following the First World War, forward-thinking naval architects and visionary commanders began to entertain a heretical thought. They imagined a vessel where the primary weapon was not a fixed cannon, but a flying machine capable of striking enemies hundreds of miles beyond the horizon. This conceptual leap birthed the aircraft carrier, an engineering feat so complex and audacious that it defied the traditional laws of naval architecture, transforming these early experimental scout ships into the unsinkable, decisive fortresses of the Second World War. Required overcoming insurmountable challenges in physics, aerodynamics, and structural engineering. The floating runway was not just a ship. It was a mechanical ecosystem of controlled violence, designed to operate high-performance aircraft in the most unforgiving environment on Earth. The initial catalyst for this engineering revolution was, ironically, a peace treaty. The Washington Naval Treaty of 1922 placed strict tonnage limits on battleships and battlecruisers in an attempt to prevent another global arms race. Left with massive, half-built battlecruiser hulls that were slated for the scrapyard, nations like the United States and Japan found a loophole. They could convert them into aircraft carriers. Ships like the USS Lexington and the Japanese Akagi were stripped of their heavy gun turrets, and in their place, engineers laid down sprawling, flat flight decks. But merely putting a flat roof on a fast ship was only the beginning. The fundamental problem of naval aviation is a terrifying problem of geometry and physics. Land-based aircraft enjoy the luxury of stationary, 2-mile-long concrete strips. A carrier pilot had to land a multi-ton machine traveling at over 100 miles per hour on a violently pitching, rolling, and heaving sliver of wood that was constantly moving away from them to solve this impossible physics problem. Engineers had to develop systems that could manipulate momentum in a matter of seconds. The most critical of these was the arresting gear. Early experiments with sandbags and crude ropes quickly evolved into a highly sophisticated network of high-tensile steel cables stretched horizontally across the aft end of the flight deck. These wires were not static. They were connected below the deck to massive hydraulic cylinders and pneumatic dampeners. When an aircraft dropped its reinforced tailhook and snagged a wire, the system had to instantly absorb the catastrophic kinetic energy of the plane. The hydraulic engines bled off the momentum, bringing a 10,000-pound fighter to a dead stop in less than 150 feet without tearing the aircraft apart or snapping the cable. It was a controlled, violent crash, executed with mathematical precision dozens of times a day. If a plane missed the wires, it faced the crash barrier, a web of steel cables raised mid-deck to literally catch the aircraft and prevent it from plowing into the planes parked on the forward bow, while landing required arresting momentum. Launching aircraft required artificially generating it. As the war progressed, aircraft became heavier, loaded with armor, more fuel, and massive payloads of bombs and torpedoes. A carrier could generate natural wind over the deck by turning directly into the wind and steaming at 30 knots. But on calm days, or with incredibly heavy bombers, this was not enough to achieve lift in the short distance available. Engineers answered this challenge with the hydraulic catapult, embedded directly into the wooden flight decks. These flush-mounted tracks utilized highly pressurized hydraulic fluid to drive a shuttle forward at staggering speeds. By attaching an aircraft to this shuttle, the ship could literally fling a heavy warplane from 0 to 90 miles per hour in a fraction of a second, hurling it off the bow and into the sky. This meant carriers were no longer just launching light scout planes. They were projecting massive, devastating strike packages. However, the flight deck was only the visible surface of this mechanical behemoth. The true operational heart of the carrier lay directly beneath the wooden planks, the cavernous hangar deck. A fleet carrier needed to house, maintain, fuel, and arm nearly 100 aircraft. Moving these fragile machines between the hangar and the flight deck was a logistical nightmare. Initially, carriers featured centerline elevators, massive holes cut right in the middle of the flight deck. While functional, they were a structural weakness and a severe operational bottleneck. If a centerline elevator broke down or was destroyed in combat, the entire flight deck was rendered useless. The ingenious American solution was the deckage elevator. By hanging a massive, hydraulically powered platform off the side of the ship's hull, engineers removed the hole from the runway. This allowed the flight deck to remain structurally intact and entirely clear for simultaneous takeoffs and landings. While planes were rapidly shuttled up and down the side of the ship in mere seconds, yet this unparalleled ability to project power introduced a terrifying vulnerability. To keep its air wing flying, an aircraft carrier had to serve as a floating bomb. Deep within the bowels of the ship, engineers installed massive, armored tanks holding hundreds of thousands of gallons of highly volatile aviation fuel, known as avigas. Alongside these fuel reserves were sprawling ammunition magazines, packed with thousands of tons of high-explosive bombs, aerial torpedoes, and heavy machine gun ammunition. Miles of complex, pressurized piping ran from the deep storage tanks up through the ship to fueling stations on the hangar and flight decks. The naval architects understood a grim reality. If an enemy armor-piercing shell or bomb penetrated the thin flight deck and detonated inside the enclosed hangar or magazines, the resulting chain reaction would vaporize the vessel from the inside out. To prevent this catastrophic fate, the carrier had to be engineered as a heavily defended fortress, leading to a radical reinvention of maritime armor and damage control. Nations approached this survivability problem differently. The British Royal Navy, expecting to fight in the narrow, land bomber-infested waters of the Mediterranean and the North Sea, designed the illustrious class carriers with heavily armored flight decks. They sacrificed aircraft capacity and raised their center of gravity to put 3 inches of hardened steel on the roof. The United States Navy, preparing for a vast, sprawling war across the limitless expanses of the Pacific, chose a different philosophy. American carriers featured unarmored, wooden flight decks to keep the ships lighter, faster, and capable of carrying much larger air wings. Instead, the Americans placed their heavy armor on the hangar deck floor, treating the hangar itself as a sacrificial space while protecting the vital engines and magazines below. because American flight decks could be easily pierced. The survival of the U.S. carrier fleet depended entirely on the most advanced damage control engineering the world had ever seen. The ships were built as a complex labyrinth of hundreds of watertight compartments. If a torpedo breached the hull, the flooding could be contained to a single small room. Engineers developed a brilliant passive defense mechanism for the highly volatile Avgas tanks, the saltwater displacement system. As highly explosive aviation fuel was pumped out of the storage tanks for use, seawater was simultaneously pumped in to fill the empty void. This eliminated the buildup of explosive fuel vapors, which were often more dangerous than the liquid fuel itself. On the hangar decks, engineers installed massive remote-controlled steel roller doors and thick curtains made of woven asbestos. If a bomb detonated among parked planes, these barriers could instantly compartmentalize the hangar, cutting off oxygen to the fire and preventing the inferno from spreading down the length of the ship. High-capacity water curtains and revolutionary chemical foam generators could be activated in seconds to smother fuel. Fires. The true test of this internal engineering came during the brutal crucible of the Pacific War. At the Battle of Midway, the USS Yorktown demonstrated the miraculous resilience born of these designs. Struck squarely by Japanese dive bombers, the carrier was left dead in the water, her boiler rooms compromised and towering plumes of toxic black smoke billowing from her superstructure. To the Japanese aviators who scored the hits, she was unequivocally destroyed. But deep inside the suffocating, pitch-black hull, highly trained damage control parties sprang into action. Operating by the light of battle lanterns, engineers sealed bulkheads, bypassed severed electrical mains to restore power, and extinguished raging fires. By pumping seawater into empty void spaces on the undamaged side of the hull, they counterflooded the ship, forcing the crippled vessel back onto an even keel. In an engineering miracle that changed the course of the war, the Yorktown's boilers were relit. Her flight deck was hastily patched with steel plates and lumber, and within hours she was steaming at 20 knots, turning into the wind to launch her fighters back into the sky. As the war dragged on and the ferocity of aerial combat escalated, passive survivability was no longer enough. The carrier had to aggressively defend itself. The fortress required an impenetrable shield, which engineers provided through the integration of revolutionary electronic technology, shipborne radar. Prior to this, ships were effectively blind, relying on young sailors with binoculars perched in the high mast to spot incoming threats. By integrating systems like the American CXAM and SK air search radars, a carrier could project an invisible dome of electromagnetic energy over the ocean. Operators sitting deep within the ship's hull in the newly invented Combat Information Center KIC could detect incoming enemy strike packages from over 100 miles away through clouds, fog, or darkness. This unprecedented early warning system allowed the carrier to vector its own defensive fighters, the combat air patrol, to intercept and destroy the enemy long before the carrier was even visible on the horizon. If enemy aircraft managed to slip past the defending fighters, they were met with a wall of mechanical violence unlike anything in human history. The late war carriers, such as the legendary American Essex-class, were bristling with the most densely packed anti-aircraft batteries ever engineered. The perimeter of the ship was lined with dual-purpose 5-inch 38 caliber guns. These massive cannons were directed by their own dedicated radar targeting computers, capable of throwing heavy shrapnel-filled shells miles into the sky. More importantly, these shells were equipped with the proximity fuse, one of the most closely guarded technological secrets of the war. Instead of relying on a mechanical timer, each shell contained a microscopic, ruggedized radio transmitter. The shell would detonate the moment it sensed it was near an enemy plane, drastically increasing the lethal radius of the carrier's heavy guns closer to the ship. The defensive screen became a dense, terrifying web of automatic fire. Batteries of quad-mounted 40mm Bofors cannons and twin 20mm Oerlikon machine guns tracked targets with relentless precision. A single Essex-class carrier could throw thousands of pounds of high-explosive lead and tracer fire into the sky every single minute. The volume of fire was so dense that it created an artificial cloud of black flak and fiery shrapnel. Diving into this defensive dome was near suicidal for enemy aviators. The sheer kinetic impact of the defensive fire could tear a bomber to shreds before it ever had a chance to release its payload in the final desperate months of the war. These floating fortresses faced their ultimate psychological and physical test, the Kamikaze. Realizing that conventional airstrikes could no longer penetrate the radar-guided, flak-filled defensive screens of the Allied fleets, the Japanese military turned their aircraft and pilots into guided missiles. It was a horrifying tactic that starkly highlighted the differing engineering philosophies of the Allies. When a kamikaze struck the armored steel flight deck of a British Royal Navy carrier, the immense explosive force was largely deflected upward into the sky. The crew would simply sweep the shattered wreckage over the side, patch the superficial dent in the steel, and remarkably, resume flight operations within a matter of hours. The American carriers, with their lighter wooden decks, prioritizing offensive aircraft capacity, suffered horrific consequences when struck. The kamikazes plunged straight through the wooden planks, detonating deep inside the hangar decks. These impacts turned the enclosed spaces into raging infernos, detonating armed aircraft and boiling the fuel lines. Yet, despite suffering catastrophic damage and staggering casualties, the exhaustive engineering focus on survivability proved its worth. Ships like the USS Franklin endured multiple direct hits, massive internal explosions, and fires that burned for days. By all logic of naval warfare, they should have capsized and sunk to the bottom of the Pacific. But the watertight integrity, the automated fire suppression systems, combined with the sheer unyielding grit of the damage control teams, kept the ships afloat. Very few fast fleet carriers were completely lost to kamikaze attacks. The floating fortresses absorbed the worst punishment imaginable and survived. When the guns finally fell silent in Tokyo Bay in September 1945, the global balance of power had permanently and irreversibly shifted. The floating runways had not merely participated in the Pacific War, they had outright conquered the largest ocean on Earth. The audacious engineering feat of operating fragile, high-performance aircraft on a tiny, pitching speck of steel amidst the vastness of the sea had been perfected through trial, error, and immense sacrifice. The aircraft carrier had evolved from a bizarre, experimental novelty into a heavily armored, radar-guided, self-sustaining floating citadel. It proved capable of projecting an entire nation's industrial and military might to any coastline on the globe. Today, the direct descendants of those World War II fortresses, the nuclear-powered supercarriers, towering 10 stories above the water and stretching over 1,000 feet long, still patrol the world's oceans, while their angled decks, nuclear reactors, and electromagnetic catapults are a far cry from the tick planks and hydraulic rams of the 1940s. Their fundamental DNA remains identical. They stand as the ultimate, enduring testament to an era when determined engineers and fearless sailors looked out at the unforgiving, storm-tossed sea and decided to build an unsinkable runway on the waves.